Hello everyone and welcome back. In part 2 I was just about to go over the shape or electron group geometry of a molecule when you have 4 electron groups. So in this video I'm going to hit on 4, 5, and if I have time, 6. So we were talking about 4 electron groups. So I talked about my analogy with the four arch enemies or 4 mortal enemies, and how they would spread around the globe. And now I'm drawing a molecule or a generic molecule to show how that would look like in 3D. This is the Earth, though the B is my central atom. That was the Earth. And then I had put my marker on the board that was going to be looking down on the North Pole. So here that's the North Pole. So we're looking down here. And then I said that the other 3 were on the equator. And so they would be pushed down. So to represent those 3, the straight line is going to be in the plane of the board. So I'm going to have one in the plane of the board here. Right, so that's going to be an A, and then I'm going to have others. Let's bring this down a little bit. Okay, so if I bring this down a little bit, okay, so there's A. So these 2 are in the plane of the board, and then I'm going to have a solid wedge here, going a little bit down. So I'm going to have an A here, and then I'm going to have another solid wedge, kind of going hashed, but it's not solid. I said solid, but it's not solid. It's going to be hashed, so it'll look like this. So then you have an A in the background there. So all 3 of these are pushed down a little bit, getting away from this one. And they're all equidistant. So this one is coming out of the board. That one is going into the back of the board. So they're kind of like this. And then this one is in the plane of the board. So you can see the 3-dimensional shape, hopefully. So then the bond angle here is going to, for all these are going to be all equally spread out. So they're all equidistant from each other. So the bond angle for this molecule is 109.5 degrees. So the bond angle between here is 109.5 degrees. Between these 2 is 109.5 degrees, and then between these 2 here is 109.5 degrees. So this is what we would call a tetrahedral angle. So I mean a tetrahedral shape. So that when you have 4 electron groups around your central atom, total, again, it's total electron groups, your bonding and non-bonding groups, lone pairs, all of them together. If you've got 4, then the electron group geometry is going to be tetrahedral. So we call that tetrahedral. And it's called tetrahedral because if you connect these together, the atoms together into triangles, it'll have 4 sides. So tetra is 4. Hedro refers to the Greek for side, hedra. So you might have heard of a tetrahedron, is a 4-sided figure. So we have a tetrahedral shaped molecule. So if you connect them all together into triangles, you'll have 4 triangular sides of equal triangles in your molecule. So that's why it's called tetrahedral. So again, anytime you have a molecule that has 4 total electron groups, the electron group geometry is tetrahedral. And so if we draw a molecule like this, so if we draw the Lewis dot structure for CH4, the way we would draw that is like this, right? So we have H, 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 H. So this is the Lewis dot structure for methane. And notice the way I draw it is that they're all at 90 degree angles from each other. That's just the way you draw it as a Lewis dot structure. You're not going to draw this in a three-dimensional kind of structure unless you're asked to. The important thing is that you're able to look at the Lewis dot structure and determine the shape of the molecule from the Lewis dot structure, not based on what it looks like on the paper or on the board, but based on the VSEPR theory, like this repulsion of the electron groups. And so, again, the idea is that all four of these are pushing each other. So again, I have 4 electron groups, all bonding groups, no lone pairs, so the total is 4. So therefore, I know that this molecule has a tetrahedral shape. Even though it doesn't look like it, I know that it has to be that shape because of what VSEPR theory says. Okay, so that's tetrahedral. So what about if I have 5 electron groups? So 5 electron groups, I'm not going to draw my analogy because it gets kind of difficult to draw. But then the idea is that, again, I'm sticking people together on a planet. So maybe I will draw another one just to kind of show it a little bit more. So here, if I have, let's say, here's my globe, right? So I have one person here in the center, right? So let's say let's draw this guy down here. So we'll draw him at the top this time. So here's your North Pole, and again you're gonna have a person down here, right? And then you're gonna have a person like here on the globe, right down here, and then you're gonna have someone on the other side as well. But if I stick another person down here, right? Let's say I stick a 5th person, a 5th mortal enemy right there at the South Pole, right? If I stick them at the South Pole, right underneath the North Pole, then these guys are going to be pretty close to him. So they're going to want to move back up, right? So they're going to get away from him. So the 3 of them are going to want to get away from him and go back up, but they don't want to get too close to them. So what's the equidistant? Right on the equator. So the 3 that were down on the bottom that I drew, now they're going to go up and they're going to be on the equator. So they're going to be in the same plane. So that's with 5. And so the way that looks in my generic molecule, if I draw it here, let's say I'm going to have B as my central atom. And so what's going to happen is I'm going to have an A on top. That's my outer atom. I'm going to have an A on the bottom. And then I'm going to have, again, this A is in the plane of the board. So the straight line is in the plane of the board. And then what I'm going to have is I'm going to have a solid wedge coming out of the board. So here's my solid wedge. So I'm going to have an A here. Then I'm going to have another hashed wedge. And that's going into the board. So I have my 2 A's here coming out of the board like this, right? So like that, they're coming out of the board. And this one is in the board. So it's making a triangle in the plane here. And then here, these guys are perpendicular from each other. So there's a straight line here. So that I have 5. So this is the shape of my molecule, or the electron group geometry of my molecule when I have 5 total electron groups, bonding and non-bonding together. So I'm looking at electron group geometry. Okay, so the shape of this is going to be Trigonal Bipyramidal. So Trigonal Pyramidal, or Trigonal Bipyramid. So that's the shape of this molecule. Any molecules that have 5 electron groups total around the central atom, that's going to be electron group geometry of Trigonal Bipyramidal. Anytime you have a total of 5 electron groups. Okay, and this is what the shape looks like. Okay, so here you have a triangle. So these three atoms form a triangle, and they're all in the same plane. So that's where the trigonal comes in. And then these guys, if you draw lines connecting these guys together, it forms a pyramid on the triangle. So you have a pyramid structure here, and then if you do the same thing on the bottom, right, you have a pyramid there. So you have 2 pyramids, bipyramidal. So Trigonal Bipyramidal is the shape or electron group geometry of when you have 5. So what about if I draw an example molecule? So let me do it over here. So I have my phosphorus pentachloride. So here, my phosphorus is central atom, and then my pentachloride is going to be here. So if I draw the Lewis dot structure, again, I have 5. So this is going to be an expanded octet, right? So I draw chlorine, so Cl, 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 and all of them have 3 lone pairs. So this is what my Lewis dot structure is going to look like. And here's the last one. So that's what my Lewis dot structure looks like for this molecule here. So again, expanded octet. Phosphorus is in the 3rd period, so it can have an expanded octet because of those d orbitals that are there in that 3rd energy level. So here is my Lewis dot structure. You'll notice I have 5 bonds or 5 bonding groups, but no lone pairs. So the total number of electron groups is 5. Anytime you have a total number of electron groups that add up to 5, then your electron group geometry is going to be Trigonal Pyramidal. So this one I know is Trigonal Pyramidal. Now, the angles here, when you have a Trigonal Bipyramidal, Trigonal Bipyramidal, you have 2 angles. You have what is called the Equatorial Angle and the Axial Angle. And if you're following my my Earth example, my Earth analogy, then the Equatorial Angle and the Axial Angle makes sense. So if this is my globe, if the central atom is my globe, then the atoms here on the equator of that globe, they form an equatorial angle. So the angles between these 3, so the angle between here and here, and the angle between this one and this one, those are all going to be 120-degree angles because they are spreading equally around the equator. So they are getting as far apart from each other on the equator. And so the only way you could spread equally around a circle is to be 120 degrees away from each other. Okay? The other is the axials. So the axial angles here are 90 degrees, right? It's because they are perpendicular to the equator. So the axial angles are going to be 90 degrees. The equatorial angles are going to be 120 degrees. So those are your ideal angles for your Trigonal Bipyramidal shaped molecule that has that geometry. I'll explain the rest in the next video, next part. Thanks for joining me.